So our speaker is Orion Ning, and he is a third-year graduate student in the Berkeley Center for Theoretical Physics in the Physics Department. He works on problems related to particle theory of dark matter and how we might be able to detect signatures of dark matter candidates using techniques in astrophysics. Short but sweet bio.
Yeah.
So please.
Thank you, Daniel. And I want to thank the organizers again for giving me this opportunity to present something very near and dear to my heart. This is what I work on as a graduate student. It's hard work, but I think it's very interesting. I guess kind of as an aside, my name is Orion. I didn't know that I would get into astrophysics, really. I originally started out as a physics student, but then slowly, the astrophysics crept in. I couldn't escape it. So as Daniel said, I'm a graduate student and technically in the Department of Physics. As a member of the Berkeley Center for Theoretical Physics. You may be wondering, what is a particle physicist doing in astronomy? That's a very good question. I think the title really says it all, from astrophysics to Axions, the glorious hunt of dark matter. I kind of want to illustrate by the end of this talk that dark matter is a very important problem, not just in astrophysics, not just for particle physics, but I think for physics in general. And hopefully by the end, you might be a little more convinced as well. Before we get into all of this, does anyone know what that picture is? Kind of one of these. If you go to this is the first result that pops up on the Wikipedia page for something. Any thoughts? Yeah, well, it's hard, right? Because it's not like something that's nice and extended, like the Milky Way. You've probably seen the Milky Way before, or you've probably seen Andromeda before, or something like that. This is actually something that's called the Coma cluster. It's a cluster of galaxies. But it doesn't look like much right now, very much, right? It just looks like some specks in the sky. And that's kind of the point, right? When we're talking about dark matter, we don't see it. And I'm going to talk a little bit more about the Coma cluster later and why this plays an important part in the dark matter story. Okay. But first, I kind of want to ask, what have you all heard about dark? It's easy as a grad student to get holed up in your office and think that everyone around you is working on these same problems, thinking about the same things, but then you go out on the street and nobody knows what you're talking about. And there's probably still a lot of people who don't really know dark matter is like one of these sci-fi things they like to throw at you, or whether it's actually real. Yeah.
Well, there's a lot of evidence to support dark matter, but we can't find it.
Yeah, exactly. Wonderfully said. Yeah.
It sounds like a kludge to explain lack of evidence.
Yeah.
It seems to be like an obscure term that you use to describe something we don't know about yet.
Yes, that's also very valid. They sometimes call this the astrophysicist sponge factor. Yes.
But you still have some clues that it's there.
Yeah. Wow. What an educated crowd. Yeah.
It might be a four-stated neutrino.
That's a very good thought, and we're actually going to talk about that throughout this talk later on. So yeah, these are all fantastic thoughts. Evidently, people know a lot about dark matter already, but we'll start from the basics here. We're going to cover a lot of ground, so feel free to ask questions, or time is running out. You can always catch me after the talk or during the stargazing session, for example. I'm happy to answer a lot of that. Okay, but maybe for a generally wider context, who really cares, right? Who cares about dark matter? Who cares about these types of problems? The cheeky answer is, if you are an American taxpayer, you should care, because part of this, part of the multi-billion-dollar kind of plans that people have for investing money in science in the United States, a fraction of that does go to dark matter, other types of research. The two articles that I put here are kind of the end results of something called the P5. I think it was called the Particle Physics Project Prioritization Panel. This is basically like an advisory committee of a bunch of particle physicists who come together and then advise the Department of Energy and the National Science Foundation on where should money be put in for the next 10 years for research in particle physics. This is important for two reasons. One, money is important for things. Money is important for running experiments, and we need to know what kind of experiments are the most promising things to look for. More deeply, though, it's also a moment of reflection for the community, right? What are the actually, here, another way to phrase, where should money go towards, these particle physics projects? Another way to phrase it is, what's the next big thing in physics? What's the next big thing we could be looking for in the next 10 years, and what's likely to be found in the next 10 years? And so these are very deep questions that people ask ourselves all the time, as scientists. In this New York Times article, you can read more about it. It's quite nice. They kind of talk about the P5 committee, and actually the chair of the committee is this guy right here, Hitoshi Murayama. He's actually a professor here in the theoretical physics department at Berkeley. So, Berkeley has a large part to play in kind of deciding the future of particle physics, I might say. And I think that's really cool. So, if you read the P5 report, there's basically, they basically narrowed down kind of these subtopics that I think are the most promising things to tackle within the next decade. And two of these are directly dark matter related. One of them literally says determine the nature of dark matter. So this is a real thing people are thinking about, and a lot of people are thinking about. The other one is search for direct evidence of new particles. This, as we'll see, is kind of intrinsically related to the dark matter problem as well. So, and actually some might argue even some of these other points are related to the dark matter searches too. It really is kind of this multidisciplinary field and problem. But again, this is also a moment of deep reflection, I think, for physicists. I pulled these two articles from Quanta. It's very nice, it's very nice science, popular science magazine. You can kind of look at the title. It says it all, a fight for the soul of science, or as supersymmetry fails, test physicists seek new ideas, or the uncertain future of particle physics.
Wait,
And
I've seen that.
yeah, that's the Large Hadron Collider.
Yeah.
Or did you read the article? Okay.
I know them.
Yeah.
They try to make they try to make dark matter with it.
Yeah. You can try to make a lot of different particles at the Large Hadron Collider. But really, what I'm trying to say here is, this is like a moment of reflection for the community, because the last big thing we really discovered in particle physics was in 2012. That was the Higgs boson. I don't know, maybe some of you remember it in the news or something. It's a very big deal for particle physicists. It's like a multi-decades long kind of project where billions of dollars were pumped into this particle accelerator. As you can see here, you've probably seen this picture all the time. It's underground in this huge, facility beneath the border of France and Switzerland. And everyone really celebrated when they finally found the Higgs boson in 2000. This is a big achievement for physics, and I think of humanity in general, some may argue. But I think the problem is that we haven't really found anything ever since. And this is a bit disturbing, right? Back in the 60s, you were popping up new particles every day. That's an exaggeration, but they were very frequent. And so now we're kind of in this period that might seem like a dead zone. Have we hit a wall in particle physics? What should we be looking for next? Because the experiments that we've tried running to test things like supersymmetry and things like that don't really seem to give evidence for new physics. And so the natural question is, where do we go next? That's kind of the more sober part of this entire program. I hope to convince you, maybe a little bit, by the end of this presentation, that I think dark matter will be the next new physics. This is, of course, my opinion, but as you can tell from the P5 report, and from people here at Berkeley too, there's a lot of people who think the same way, and a lot of research effort has been devoted to looking at dark. And there are reasons to be optimistic, and I'll go over some of them. One, as someone said, we know that it must exist. This is actually very important. There are a lot of things in physics that we don't really know exist, but dark matter is one of those things that we know has to exist in some way. Otherwise, because we don't really have a way to explain it. The other thing is, from these observations, we can infer a lot of the properties of dark matter. Sometimes it's just as important to know what dark matter is not as it is to know what it is. And there's a lot of efforts that have been done for this. There's also a lot of very motivated theories to test, right? And the particle theory, kind of landscape is people that come up with a lot of very interesting things in particle physics that would shape our understanding of, what the fundamental particle world looks like. And these things can actually be tested in the dark matter paradigm. So that's very exciting. But the most important thing that I think is relevant for here and now is we are in the middle of a golden age of data. This is unprecedented for someone who was living in the 60s or 70s or 80s, right? When the dark matter problem was just starting to emerge and be taken seriously. We have so much data from particle colliders, from experiments, from telescopes, from simulations and things like that. We almost don't know what to do with it, right? But we have so much data, and we can actually go look for particles in this data, and that includes dark matter. And I think this is now only starting to be truly appreciated in the context of this problem. And I think it's very exciting. So dark matter, to summarize, kind of has a legendary past, as we'll kind of go see, a very busy present, right? There's a lot of busy grad students in this day and age, unlike me, and then an exciting future ahead, which I think gives it a renewed sense of optimism in the 21st century. And this is why I'm personally very excited. And then I call this a glorious adventure because I think we'll learn a lot from this problem, even if we don't find out exactly what dark matter is. Okay, without further ado, let's get into the meat of things. Again, I'll be covering a lot of ground, so feel free to stop me if you have questions, or you can always chat with me after the talk. The roadmap that we're going to follow in this presentation is split into 3 chapters. The first chapter is astrophysics. What do we already know about dark matter? Okay. Chapter 2, now that we know things about dark matter, particle physicists will come in and try to answer what can it possibly be, right? And then the third thing, which I call science, is how do we go and look for it? And I think this is important, right? This is what they tell you in like 7th grade science fair or something. Like you should go have a model, have a prediction. You go out and actually collect data for it, and then you test this on your model. And you can see whether it supports or rejects your model. Now I think in this age of data, we're finally appreciating this last one for the dark matter problem. Okay, so let's start with chapter 1. Astrophysics, what do we need? To illustrate this, I'm going to go in depth on 2 kind of historical anecdotes about how people came to understand a little bit more about dark matter and how we know that it must exist. And I'll talk a little bit about some other things later on. But the first one, which is roughly chronological, has to do with the Coma cluster, which I flashed a little bit at the beginning.
Those are a lot of galaxies.
Yes, they are a lot of galaxies. In fact, I think there are like thousands of galaxies in the cluster. And this was this kind of entire thought experiment was first thought of by a guy named Fritz Zwicky. He was a Swiss astronomer. He was very famous. And he basically looked at the Coma cluster and had the following thought experiment. He basically was interested in how the Coma cluster was forming together, and he asked himself this question: how do the galaxy speeds play a role in the formation of the cluster? And every time I have a question mark here, maybe I'll ask the audience if anyone has any preliminary thoughts on this. What does galaxy speeds have to do with how the cluster forms? Maybe that could be it could be a complicated question. It might be a bit tricky.
Yeah.
Oh yeah, please.
Galaxy speeds could create more galaxies, they could collide, and also galaxies going faster, like catch other galaxies going faster.
Yeah, exactly. I mean, you're getting to a very, very important point, which is that it basically has an effect on other galaxies, right? There's galaxies that can move very fast, very slow, that you can like collide or like fly away from each other. What Zwicky thought back in 1933 was the following. He said slow galaxies basically don't move fast enough to escape the cluster, so they get captured by gravity. Right? A cluster is made up of many galaxies. You sum up all the masses of the galaxy, you have a pretty strong gravitational force that pulls the cluster, other galaxies that are slow moving in. Right? On the contrary, fast galaxies will fly away from the cluster. Right? If you're fast enough, then you can escape the gravitational. You have enough energy to escape the gravitational bounds, and then you can escape and be your own free agent, no longer bound to the Coma cluster. This is kind of akin, I like to think of basically, you have like a bunch of flies in the room, and you have a vacuum cleaner, and the vacuum cleaner is gravity, and you try to suck in the flies. If the fly is very slow moving, it's easy to suck it in. If the fly is very fast moving, you're probably not going to suck it in.
And it's gonna escape the room.
It's exactly, it'll escape the room and then cause problems. And maybe probably breed more flies. So basically, he thought about this mechanism, and he says, okay, well, I can go out and measure the speed of the galaxies. And then that will tell me, in order for this cluster to exist, what kind of mass must they have in order to keep everything together? Or put another way, the Coma cluster has to have a certain mass in order to keep some of these fast-moving galaxies still bound to the cluster, because that's what we actually do. Okay, so if you see a very fast galaxy that's still bound to the Coma cluster, you should have a very large mass for the cluster in general that's strong enough to pull it in. Okay.
It's different depending on how much mass the cluster has.
Yeah, exactly. And this is what he was trying to test. When he, measured the actual galaxy speeds, he basically could make an estimate for what the mass of the galaxy must, mass of the cluster must be. And he found that actually, very disturbingly, this mass was around 10 times the mass that you would get just by looking at starlight. Okay, so this was a big deal at the time, right? It basically means there's a lot of this unaccounted for mass that must exist in order for this cluster to exist, but we don't see it. You know where this is going. He knew where this is going. He was actually one of the first to call this dark matter, or in the original German paper, Dunkel Materie. I guess, I don't speak German. But that's basically, he was, I think, amongst the first to give this name dark matter, basically this thing we don't understand and must be causing some extra gravitational effects in this cluster. Okay, so if you're not convinced in 1933, I mean, if you're not convinced, so were many people in 1933. I think really the dark matter problem became a lot more, people began to treat it a lot more seriously, more convincingly, with the work of Rubin and Ford in 1970.
That's Andromeda.
Yes, that's Andromeda.
That's the galaxy that's gonna crash into us in like 4 billion years.
Correct. Hopefully not in our lifetimes.
Definitely not in our lifetime.
Yes. The Andromeda galaxy is very beautiful, right? This is probably something people have seen before. Basically, what Rubin and Ford did, Vera Rubin, by the way, very famous astronomer, underappreciated at the time as a woman astronomer in the 70s. There's a telescope that's named after her, Vera C. Rubin Observatory, some of you might have heard of in use. Anyways, they did this very seminal work. That was actually initially supposed to be an uncontroversial problem. But as we'll see, it became very controversial. What they basically were wondering was, I want to catalog the speeds of stars across the galaxy. Look at Andromeda, and then I have stars that, maybe one located near the center where, all the stuff is, all the matter is, one that's a little farther away, and then one toward the outer reaches
That's
of the
like
galaxy.
the spinning, yeah, that's kind of like the galaxies with the clusters.
Yeah, in a
Is
sense,
it
you're
the
basically
same?
measuring the speed, right?
Is it the same with the rotation too?
In a sense, they all try to do the same thing, which is just measure the speeds of astronomical objects in something that's supposed to bind them all together.
Are like the farther stars away faster, or are they slower?
That's a good question. I'm going to ask the audience that in a bit. But the thing that Rubin was trying to think about is what will be the speeds of these stars, right? If you have one toward the center, if you have one toward the middle, and you have one toward the outer reaches, what you'd expect it to be. It's a very educated audience member in the front kind of alluded to, this may not be exactly what you think. But I guess naively, the way that I think about this is, let's look at our own solar system, right? I think the solar system we can understand a little more concretely. This is a very misleading picture, right? Because the sun is actually much bigger than all the planets. But let's assume that it's very big. I think it's not hard to intuitively understand that when you have like Mercury, it's very close to the sun. It gets pulled on by its gravitational effects the most. So it spins very, very fast, right? And then it spins much faster than Earth, right? Earth is a little farther away. It feels the effects even less. And you go out to like Pluto or something, and it feels the effect the least, right? Even though I guess Pluto's not a planet, so I can't really consider a planet, but it's a planet in Arizona.
To be a planet.
Yes, and I think it's still a planet in Arizona by some like, congressional laws. But this is something you can look up. But anyways, Pluto it will be moving very slowly, right? It's not feeling the effect of the gravitational mass of the sun very much. And in some sense, you can think about it like we exist on Earth. We're bound by Earth, but we're very close to Earth. That's how we stay here. But we don't really care what's going on in Mars, right? Because that's so far away. So the same story can be said of these stars, right? Naively, you would think that you should have slower rotation speeds near the edge. The things that are closest to the center get pulled on by the gravity of the galaxy center the most, and so they should be going very fast. As you go farther out, where you feel these gravitational effects less and less, and so then these stars are, should be very slow, right? But of course, that's not what we see. That's not the common knowledge anymore. Now,
That looks like
what was basically observed by Vera Rubin, that's her down here in the bottom left, was that the gravitational all these stars happen to move at the same speed. It doesn't matter where you were in the galaxy. To rough first order, everything moved at around the same speed. This is kind of expressed in this rotational, these galaxy rotation curves, which on the y-axis gives you the speed of the star, and the x-axis tells you how far away from the center, right? You should expect, you should expect it to go like something like this, right? The farther away you are, you should be going slower and slower, but they actually find something that's roughly, flat. And so this is very surprising, very
Can I ask a question?
Yes.
Why is that called a galaxy rotation graph when you're actually looking at how fast the stars are moving?
Because the stars are very roughly, yes, the stars can have their own motion, but they're roughly being pulled by the same, I guess, it's kind of like a fluid motion. Yeah, it's like a fluid motion of this galaxies that's still that's responsible for most of the stars being.
Okay.
Yeah. Yes.
Why is there a dip in the curve there near the y-axis?
Oh, near the center?
Yeah.
Like over here?
Yes.
That's just from other types of effects. So there's more complicated things that go on for the galactic center. So that's near that's big. This is you're talking about like this area,
Yes.
right? Yeah. This is something that again is due to like more complicated effects in the galactic center. There's to my knowledge there are like these things like you can have I guess like baryonic feedback they call it, where you can have like matter that comes in and then like it pushes things out. You can have very dynamical things that happen in the center. I'm not an expert on it. I think maybe there was a talk last month about the galactic center that can probably talk a lot about the things that happen. But I think, and for this particular problem, the overall effect is still the same. That it's mostly, yeah.
What's the vertical axis label?
Rotational velocity in kilometers per second.
Rotational velocity, kilometers. Okay.
Yeah, so if you look at a point,
Talk about radians per second.
yeah, it's talking about actual like speed, like a car. Yeah. Yeah. Anyways, yeah, good questions. These are very important to understanding topics. I don't think it was very intuitive at the time, and there was a lot of people that didn't believe it, right? But I think over time, people have kind of accepted this, and you can actually see it with more observations, right? So the story didn't just end with galaxy rotation curves. Obviously, you've heard the rotation curve story, but there's more to it that developed in the next few decades. There's also kind of the case of the bullet cluster that people like to point to. I'm not going to go into these in great detail, but the bullet cluster is basically the idea that you have two galaxy clusters are colliding toward each other. The gas stops, like kind of gets slowed down because it's hitting other gas molecules. But if you look at where most of the mass is, they seem to pass right through each other. So there's another evidence of dark matter. There's also the coma cluster case that we looked at earlier, is responsible for binding the coma cluster galaxies together. There's also effects called gravitational lensing, which is basically say if you have strong enough gravity, you can not just pull down humans, you can pull down light as well. And so light will actually warp because of gravitational effects, and it can warp around dark matter. And then structure formation basically refers to the case where people have done a lot of like simulations and studies about how dark matter was actually responsible for like formation of galaxies and galaxy clusters in the early universe. It had enough mass to pull things together and actually bind them coherently into things that we know as galaxy clusters. And these are like some simulations that are very famous. And then there's also like evidence in the cosmic microwave background, which I definitely won't go into detail very much either. But it's basically the sense that there's like this thermal relic of like microwave photons at the beginning of the universe, and then an early universe effect will be affected by dark matter kind of evolving, and then it would leave imprints. Yes.
Why's the picture for the structure formation like blue things?
Okay. So if you were to go into detail, these are simulations. Each box is a simulation at a certain era of cosmological time. So a certain era of the universe's history.
Also, like the higher ones are lighter, but the lower ones are darker.
Yeah. So that's the point. So the point is, you can go from top to bottom. That means time is going forward. So the blue thing represents a collection of dark matter. So you start in the early universe with like a hot soup of dark matter. The universe was very hot and dense back then.
Also,
And then it like slowly picks, start to, condense into networks that develop into the network of galaxy cluster we see today. Yeah. Good question. Yeah. So let's see. All of these things basically told people that over time, the very surprising and bizarre fact, which was that actually most of the matter around us should be dark matter, 84% actually. In fact, things like you and I were only 16%. And this 84% is, what would be responsible for, a lot of the effects that we see, like rotation curves and, invisible matter, like this invisible substance that we know has to exist, but we don't yet quite know what it is. Yes.
it's kind of weird how most of the matter that's invisible is actually most of the matter is invisible, and the rest, and the ones that we actually can see, is just a tiny little chunk of it.
Yes, very weird. This is why people are very bothered, right? How can you really believe something you can't see? If I were like in, maybe if I was like a dog or something, I wouldn't believe it. It would never cross my mind. But like, we know this because of influence, right? I mean, we know it has to have an effect because of things that we measure, and then that's how we figure out things that we can't see. Yes.
Do all 6 of those support like the numbers of 84 and 16?
That's a good question. I'm not sure. I'm not an expert in each of these things. I suspect though that many of them will. I'm sure there are like some parameters in these things in which you can tune that you might be able to get to that number, but I'm not actually 100% sure.
Okay.
Yeah. Okay. Great. So that's the astrophysics part. The next chapter is kind of where these particle physicists come in and they ask, well, what can it possibly be, right? What is this thing that we can't see? What is dark matter really? Particle physicists, they want to know the fundamental nature of things around them at the smallest subatomic, fundamental particle scale, right? And so when they see this new problem, there's this dark matter, they want to ask, okay, is this like some particle I've never seen it's never seen before that I can actually observe? Before we get to that, I'm going to talk a little bit about what has been known so far. It's kind of this catalog that was constructed over the last century about fundamental particles that we discovered. People write history books about it. Each has its own glorious story attached to it, and often gives new, often unexpected results that change our fundamental understanding of physics. Every time something new is discovered, and this catalog of particles is called the standard model of physics. And of course, then the question then that people were asking is dark matter going to be the next particle physics discovery? And something I alluded to at the beginning of the presentation. I find the situation akin to, if you were, like a young child on Christmas Eve, and you suddenly hear Santa Claus coming down the chimney, putting some presents under the tree, and you decide to get kind of naughty, you go down, right, and you want to open, you don't want to open the present, right? That probably brings a great misfortune and like disciplinary action by your parents. But like, let's say you wanted to guess what it is, right? You pick up the present, you can shake it, you can weigh it, you can, maybe if you're very creative, you can put a magnet against it or something, right? And then throughout all of these things, you're trying to figure out what's inside the box, but you cannot open it. And that was kind of the stage, that people were dealing with back when the dark matter problem was presented, right? We know that there's a box there, there's a present for us, hopefully. But when we can like shake it, we can like weigh it and things, but we don't really know what it is. This bothers, if this bothers you as a kid, trying to open up a present, but not really open up a present, it's a very bothersome for these physicists, right? Who are trying to figure out what this dark matter stuff really is. Okay, so let's begin with a very quick one-slide summary of the standard model of particle physics, right? Before I say anything, maybe I can query the audience. There are some very enthusiastic members here. What particles do you know of? Things, yes.
The Higgs boson.
Yeah, the Higgs boson. Great. That's the one that was most recent discovered. Yeah.
Fermion.
Fermions. Yes, that's a class of particles that encompasses many, but yeah, that's a fundamental class of particles. Yes. Quarks. Fantastic. Yeah.
Leptons.
Leptons. Yeah, that's another great class of particles. That's part of the standard model. Yeah. Neutrinos. Yeah, you guys are basically covering all the ground. Yeah.
Gluon.
Gluon. Yeah. All these funny particles you've probably heard of before. Again, very educated audience. This is a table I pulled from Wikipedia that basically lists the the standard model of physics. Not counting like antimatter because that's just like a mirror of it. All of these particles are particles that we know exist and we deem like the fundamental particles that we know of too. Right? This is all of human knowledge about particle physics into these 17 particles. I think 12, 14. So yeah. Yes.
It's just that is a proton a particle?
Excellent question, actually.
And what is it called? The minus particle? The electron? Oh yeah,
Oh,
electron.
yeah. So fantastic point. Actually, this leads me right into the next section, which is
Don't they make
a lot of the
atoms?
knowledge. Sorry.
They make atoms.
Yes,
Right?
there's an atom right here. Yeah. So you already jumped the gun, but this is the natural transition, right? To a lot of what we know about fundamental particles comes from the atom, right? The electron is probably the most well known, right? You learn about this in school. It has like a negative charge. It orbits the atom, kind of, and it basically is responsible for like making things work, like electronics, right? Because of its charge. Quarks basically are these subatomic particles that may not be known to many people, but they make up the things that are known to people, like protons and neutrons. So protons and neutrons turn out to be these, composite particles that are made up of these little things called quarks. Quarks is a very funny name. They have very funny names like up, down, strange charm, bottom, and top.
Oh yeah, I've heard
Each
of
of them-
strange quirks.
Yeah, each of them kind of has their own history. The name Quarks itself, I think, was from some James Joyce novel, which I think he's an author that's frequently known for being a little incomprehensible. But anyways, that's where the quarks come from. They make up, things in the nucleus, right, of your atom. And then they're glued together by what's known as the gluon, right? As someone alluded to earlier.
But
Right.
glue.
Yeah, exactly, like glue. So this glues all the quarks together into like things like protons and neutrons and things we know today. This all happens at the atomic level. Here's a fan favorite. The photon is basically light. Yes,
Light particle.
fantastic. Yes, it's basically light. This is responsible for like electromagnetic interactions. And then there are these things like the W boson, the Z boson, neutrinos. These are involved in something called the weak decay. So by the way, the gluon and like the quarks are involved in some theory called quantum chromodynamics. This is basically a fancy word for the strong nuclear force, which is another fancy word for basically the thing that holds atoms together. We call it a force. It's a fundamental force. It's very strong, as the name implies. Called the strong nuclear force. I'm not making that up. Back in like 8th grade, apparently, when the science teacher was asking people, hey, what are the, can you name some like fundamental forces? People say gravity, people say electromagnetism. I read ahead and I said the strong nuclear force, and everyone laughed at me because they thought I made it up. But it is called a strong nuclear force. And correspondingly, there's the WZ bosons, like neutrinos, and some other leptons take part in what's called the weak force. And the weak force is responsible for like radiative decay. So I think, I could, there's like a standard process, I think, called like beta decay, in which you can have like a neutron that decays into like a proton, an electron, and a neutrino. Yes.
Why is the Higgs boson yellow?
Why is the Higgs boson yellow? It's yellow in this diagram. I don't really know what color it is in real life.
Why is it yellow on the diagram?
Because I think it has a lot of properties that are very different from the rest of it. So they're the color, maybe you're asking about the color scheme. They're colored based on like properties that we all share together within each color.
Something like with
Yeah, so sorry?
they have something that all of them have. Like
Yeah.
all the green ones.
Yeah, exactly. Right, and they have the labels here, right? These are leptons, they're quarks, gauge bosons, and the Higgs boson. Each of them share a lot of properties within each color. So that's a good question. And then the Higgs boson was the last thing we discovered. I put an elephant here because this is kind of the thing that's known for giving mass to the other particles. There's a mechanism called the Higgs mechanism, in which the Higgs boson basically lets all these other particles become heavy. So it's very, very important to light as we know it. It was also the most recent particle discovered, again, by the LHC in 2012. And unfortunately, we haven't really seen much beyond this diagram ever since. But it was a big achievement at the time. I think they should be very proud of discovering the Higgs boson. So the natural question to ask is, where is dark matter, right? Kind of the upshot, if people have thought about this is the immediate thing they thought about, is the standard model can't explain what we've observed from dark matter, right? None of these particles can really explain kind of this large gravitational, very weakly interacting thing that's causing galaxy, rotation curves to be the same or causing clusters to be held together. For example, let me give you an example of why this can't be the case. What if dark matter was all made out of electrons? This would be very strange because electrons are charged, right? And so you should expect a lot of electromagnetic interactions from like clusters or galaxies if dark matter really was made out of electrons. But we don't see light. We don't see any kind of electric, like kind of gradient at all, like some E&M gradient. So it can't possibly be the electron, right? And people have run through this thought experiment for all the other particles, and they've determined that you can't really make dark matter with these things that we have right now. There are also some other problems in the standard model. The standard model is like known for being complete, but not really. It's what we know so far, but we know that it isn't the full story, not just because of dark matter, but for many other problems. But yes.
Is there anything to do with the graviton that could explain it?
Yes, the graviton is a hypothetical particle, right? That's supposed to mediate gravitational forces. Typically, I think there are two classes of people, particle physicists. One that just deal with these things and not the graviton. And then two people who just deal with the graviton. Right? And because I think the problem is it's a very hard problem because gravity is so weakly interacting, and then nobody understands what a quantum description of gravity is. All the gravity that we know today is actually still basically what Einstein originally proposed like 100 years ago in general relativity. But like to make it quantum, to have it like obey things that we understand at the fundamental level, nobody really knows, and it's very hard to test. And so we're not going to talk about the graviton today, but I guarantee you there are people who think about the graviton and dark matter. Yeah. Yes.
I was wondering why they still think of gravity as a force, because didn't Einstein say
Yeah.
it's a
Exactly,
warping of space and time?
Yeah.
So why are we looking for a graviton? Because
Yeah.
it's not really a force.
It's the
It's
same.
geometry.
Yeah, the same was true, right? So what you're referring to is that general relativity, as proposed by Einstein, is a field, right? It's about the curvature of space, right? Kind of an analogous story happened with E and F, right? People really didn't think that the photon was responsible for like light and electromagnetic interactions. They just thought of it as like kind of a field that permeated everything. And this is exactly the same analogy. Now that we've been able to isolate like single photons in a quantum theory, like in experiments, we are more determined that the photon is an equally valid wave with like electromagnetism. But we don't really know how to do this for gravity. It's too weak. Yeah.
Actually, going back to your previous slide.
Yeah.
And you talking about photon, isn't the photon is really the only thing, basically the only thing astronomers.
Yeah, exactly. Yeah.
So it's kind of going to the question of, so why is that 15% so doggone bright?
Yeah, that's a very good
Difference can you
question.
make based on only one of this panoply getting into your telescope.
Yeah, maybe it'll be a bit more clear when I talk about like detection methods. So I'll talk about that in astrophysics. If it's still not, feel free to bug me after that. But yeah, you're right. It's like, this is the one thing astronomers have, right? They basically just have light. And then, but the thing is that light's very important, right? Light isn't just like a number, right? Light, there's polarization. There's like different wavelengths of light. There's different amounts of light flux, right? So you actually get a lot of information about light, and a lot of modern astronomy is underpinned on this. Just how much can we prove with just light? That's why it's very powerful. But yeah, maybe when I talk about like indirect detection later on, and like how we might look for these things in astrophysics, these questions will be a little more clear. Okay. So we don't really know what it is. So this is kind of the Oppenheimer moment where you get up to your chalkboard and you try to think about some new way to revolutionize physics, right? With a new particle, right? What do you think that most physicists would like? Where do you even start with such a problem? How do you even start? If you're trying to come up with a new particle. Wild guesses, yeah.
Well, start searching the particles you already know and find some missing components that seem like should be that, or that seem like they should be.
Yeah, fantastic. That's I'll discuss that as well. That's what colliders do. That's one valid way to do dark matter. Yeah.
Not entirely sure if this is dark matter or dark energy, but isn't there some like really deep underground detector that kind of sort of maybe works?
If you're referring to Dune, deep underground neutrino experiment. Yeah. Yes. This kind of sort of maybe. This is a very controversial experiment for many of you. But yeah, some actually. Well, I'll show a slide later when I talk about like one of these kind of candidates that has to do with neutrinos, and that actually becomes somewhat relevant. But yeah, that's a very good way of thinking about it. Like from things that we already know, how can we naturally extend it? Yeah.
Wimps and machos.
Yeah, wimps and machos. That's great. Actually, I'm going to have a slide about wimps in just a bit. And I'll explain what a WIMP means. But basically, these are like classes of particles that people come up with to try to explain dark matter, right? It's very exciting. You can come up with all sorts of stuff. But let's first come up with a systematic way of organizing it. I'm going to put a chart up. It's going to be very complicated, but I'm going to help you digest it. This is a ruler for what possible mass dark matter can have. Okay, so we just need to understand on the x-axis, this is the possible range of masses dark matter can have. It's in this, there's things I need to mention. It's in this funny unit called an EV, electron volts. I'll talk about that in a bit later, why we go to electron volts. But the first thing is that this is in scientific notation. Maybe some of you are unfamiliar with scientific notation or have forgotten it. But basically what that means is like something that's 10 to the 30 means like a 1 with 30 zeros in it. An insanely large.
Is that for each particle?
Yes, so this would be the mass of a single particle. And so 1 with a 0 with 30 zeros after, that's like crazy, right? But it's in units of electron volts, which I'll mention in a bit. That makes it a little less crazy, but if I were to go to the doctor and say I'm like 10 to the 30, no units attached, they might be a bit concerned, yeah.
Why are the tiny numbers above 10
Ah, yeah,
going
that's
by
next.
3?
Yeah, so this is just a scale that basically says there's gonna 7 and 8 inside, but because you don't want to overcrowd the x-axis, you just do it by 3.
Just do it.
Yeah, and so on the other end, 10 to the minus 21 means you have a 0 point and then 21 zeros after until you get to a 1. So that's something insanely small. I'm doing this to give you a sense of how big the ruler is because we don't know where dark matter could lie in this ruler. Right, here's a sense of scale. These are not actually the mass of these things, but imagine if you have a drop of water that's placed at the location of 10 to the minus 9. You go up, this is called an order of magnitude, 25 order of magnitude, so around 10 to the 15. That's the equivalent of saying a drop of water is to all the water in the oceans. And that's not even like, that's like just half basically of this entire scale. So this is all just to say that it's a very, very wide scale of what kind of dark matter particle can be. Okay, but why are we using this funny unit? It's an electron volt, but maybe in something that's a little more familiar, there's a little conversion up there in the relevant region of mass of something in grams. Okay, this is America, so maybe I should have put it in pounds. Let's not complicate our lives a little. No, we don't need to complicate it more than we need to. Let's say, on the far right here at like 10 to the 30 eV, this is about the equivalent of, maybe like a few grams, and that's like a mosquito weight. Okay, this is like the mass of a mosquito. So the mosquito would lie all the way over here. You go even smaller, you get to like the nanograms, 10 to the minus 9 grams, and you get to a cell. That's like 10 to the 24 eV. Right, so you're starting to get smaller and smaller. As you get to a strand of DNA, that's around like 10 to the 21 eV. Right, naturally, when you're talking about subatomic things that should be smaller than DNA, for example, should be smaller than like atoms, you want to, you really do want small things, and that's why the EV scale is useful. By the way, EV means an electron volt. This is basically, technically, the energy that an electron picks up as you put it through 1 volt of potential difference. Yes.
Just out of here, I don't know if you can do it on the fly, but so where would the total mass of the observable universe be?
The total mass of the observable universe.
Just.
Yeah.
That's a good question.
Let's see. I know that the supermassive black hole, the center of the galaxy, is like 10 to the 6 or 7 solar masses, which means 10 to the 6 or 7 times the total mass of the sun. Let's say. Okay. Actually, our galaxy is like 10 to the 11 solar masses. If you include dark matter, it's 10 to the 12 solar masses. That's just for our galaxy itself. And then if you include all the galaxies, that number becomes, I don't know, like 10 to the 20, 10 to the 30, 10 to the, it's hard. It's very big, very big. I don't really know the number off the top of my head, but I hope that helps a little. Yeah.
Why is there negatives for the tiny ones?
The negative just means I'm putting 10 to a power of a negative number, which means that it's going to be a very small number. Yeah, again, so 10 to the minus 21 is like a 0 point with 21 zeros. That's just the notation. Anyways, an electron volt is useful though, right? Because, I guess I mentioned that the electron volt is actually a unit of energy. Like when most people see it, like it's the electron picks up some energy as it goes through 1 volt of difference. And you might be wondering, what does energy have to do with mass? In particle physics, all of these things blend together. And actually, you can think of, for example, the case of Einstein's famous E equals mc squared, right? This basically says if you have some mass, it basically is some unit of energy as well. This is the origin for the atomic bomb, right?
What are an electron and a proton?
Oh, fantastic. I'll get to that in the next slide. The next slide is standard model particles, right? So here you can see like the electron, that's the E up there. I don't know how hard that is to see. The E lies at around like 1 MeV or like 10 to the 6 EV. So the electron is kind of like squarely in the middle of this ruler. If you go up, then you'll get something slightly heavier. You'll have like quarks, right? And multiple quarks together form like protons. So that's like another, order of magnitude or so up. Then you get to like the muon, the tauon, the WZ boson, the Higgs boson. These all within the confines of this red box that lies between, well, that side is not actually as well determined, but like maybe like 10 to the 12. This is like the neutrino here. The neutrino we know has a mass, but we don't know what mass it has. I'm not a neutrino expert, but this is what I'm aware is the story. It's very, very light. As you can see, it's actually separated quite a bit from the rest of these particles. But we know from neutrino experiments, which I think got a Nobel Prize like a couple decades ago, it must have some kind of mass that is very, very small. But we know the neutrino is a definitely real thing, right? It's not like a dark matter. the kind of effect that we don't know what it is. We actually can measure neutrinos. So this is all the particles that we know today, and that's why this rule is very helpful, right? It's right in the middle of this. So the natural question meant to ask is, where would we look for dark matter? Trick question. Everyone looks everywhere because we have no idea what it is, right? And there's some that have funny names too, actually. I'm going to go over a few of these, but I kind of want to. This is a very nice plot by someone named Orion Ning. He categorizes it into things like wave-like particles and particle-like particles. What that basically means is if something is like relatively heavy enough, you can say it's like a particle. Like we think of an electron as like an actual particle. Right? There's a lot of caveats to this, but let's think of it that way. If you have something that's wave-like, it becomes so light that you can almost think of it like as a light wave or something. And these things have different effects. Yeah.
Could, how do they rule out the fact that, well, that a neutrino is not, it can't be dark matter?
Neutrinos are too light. That's
Too
why.
light.
Yeah, because we know gravity, dark matter exists because of gravity. You must have a bizarrely amount, crazy amount of neutrinos to even have a chance of maybe constituting dark matter. But we don't think that's possible for other reasons. But the short answer is that neutrinos are way too light. But this is something that people thought of. Actually, one of the first things they thought of, because it looked like it would have been a good candidate. It's like saying, I'm going to add up a bunch of light waves together, because it's almost like a light wave. But that doesn't really give you enough gravity to do anything. And so that's why they kind of abandoned normal neutrinos. Yeah.
Is it just out of curiosity, is there a name for like that chart just for later research? Like,
Yeah, if you you can look up if you look up like, I don't know if this chart has a special name, but you can look up like a dark matter mass and then look up this guy, Orion Ning. He has like really great charts for dark matter. Yeah.
Have you ruled out in this discussion of primordial black holes?
Primordial black holes, would be like around here. They're considered part of composite macroscopic dark matter. Yes.
What are those letters at the top?
Those letters are Greek prefixes for EVs. So something that's like big MEV stands for mega EV. That's basically shorthand for, if you do a vertical line at the bottom, 10 to the 6. It's like, computers, megabytes, gigabytes, petabytes, things like that. Yeah.
am I allowed to take a picture?
Yeah, please. Yeah. But yeah, the bottom line is, we don't really know what it is. So people go searching everywhere. You can have things that are very light and things that are very heavy. And again, some of them have funny names like Wimpzilla, I guess. But we'll talk about some of these in detail. So I find this akin to going to a zoo, right? This is a map of the Oakland Zoo. I go around and there's a lot of different exhibits of very, very different animals, right? And these animals have very different personalities and they're very different characteristics. But which one is dark matter? Is it the elephant? Is it the tiger? Is it the goose? Nobody knows. I guess there's a goose on here. So I'm going to kind of go through, I think, a few of these exhibits, and then we'll kind of go into what people think about what are some of the most motivated candidates today. Number one is WIMPs. WIMP, very generically, a weakly interacting massive particle. It's a very generic. It's actually one of the first models that was proposed, I think, in around the 70s and 80s. And it's a hypothetical massive particle that has many generic properties that interacts via gravity and very weakly to the rest of the standard model particles. Funny, a good thing about WIMPs is that there's a lot of models in which they can self-annihilate, and that means they can produce signatures. So in this diagram down here, you can have, let's say, two dark matter WIMP particles, they come and collide together, and then they transform, and their collision causes things like photons to escape out, electrons, positrons, things that we might actually be able to. And this is kind of the search that goes on in this diagram here. When you look at the galactic center, this is a radio picture of the galactic center by the VLA. It's a very pretty picture, but there's a lot of violent events that go on, right? I think, again, last month's speaker talked about the galactic center, but there's a lot of things. There's stars that are starting to come together. There's a supermassive black hole that's eating things up, causing accretion. Some might say that there are a lot of WIMPs near the galactic center that's also creating radiation as well. We might be able to observe. This is something that people go out and look for. And this is on the kind of the more heavier side of things. So if you were to look at this chart, it'd be right here. They're also appealing for other reasons. Cosmologists, their arguments in cosmology and their arguments in theories of physics like supersymmetry that say that a WIMP actually is a really great candidate to satisfy these types of models. Supersymmetry, I have this funky diagram, is basically, I'm not going to go into supersymmetry very much, but it's basically like saying you have particles and there's a mirror image of these particles. that have the opposite type of properties. And supposedly, when you combine all of this together, it gives a more unified picture of physics in general. I'd say that supersymmetry, again, is probably not as popular as it was 20 years ago. There are still some people that work on it holding out hope, and the WIMP might be, one of these hopeful things that they wish for. One example of this, for example, being the Higgsino, which I think is still a very motivated particle candidate that requires some amount of supersymmetry that people are looking for today and really think it might be dark matter. Yeah.
In the early 80s, there was the WIMP miracle.
Yes.
And which was the mass of WIMPs was predicted to be something, and it matched what they thought the astrophysicists thought
Yeah.
would be the mass of all the dark matter.
Yeah, exactly.
And that led to a long 20-year period of looking for WIMPs. And they've never been found. And supersymmetry is a beautiful idea, but it's an idea. And it
Yes.
never has been proved.
Yeah, exactly.
So I think a lot of physics has moved beyond it.
Yes.
It's a great theory.
Yeah.
It wasn't true.
Yeah, a lot of the, I mean, that is true. Everything about that is true. Many WIMPs have already been ruled, right? I think maybe people talk about like funny things, sounding things like Benos and Minos. These have kind of been ruled out in astrophysics. The reason why I mentioned the Higgsino is because this is kind of the last man standing with the WIMPs. And this is kind of the last things that people think about when they consider WIMP dark matter, because there are still mechanisms for the Higgsino to escape all these non-observations. Yeah.
Is there any reason why like it does have the word Higgs in it? Like, what is it related?
It's supposed to be like a super partner of the Higgs.
Super.
Yeah, so it's related to the Higgs very intrinsic.
Okay.
Maybe for lack of time, I'll start to go a little bit faster. Let me go to the next exhibit here. Next exhibit we've got is sterile neutrinos. So as someone talked about earlier, neutrinos were actually a very popular candidate, but they're too light. Therefore, let's come up with a heavy version of it. Okay, that's basically what that sterile neutrino is. It's called sterile because they're not active, because we don't really measure them very easily. Their heavy counterpart, it would kind of, if you go deep into the theory, it would explain why active neutrinos have such a small mass and why they had mass in the first place. This is something called the seesaw mechanism, which is kind of funny. It's like if you have a really big person, on one side of the seesaw, the other person who's very light will get lighter and lighter as the other person, goes lower and lower. So they think, given the light neutrino, you can have a very, very heavy sterile neutrino counterpart that we haven't yet observed. So someone mentioned or alluded to Dune. This is a diagram, I think, from Dune. Yeah, because that's Fermilab right there. And it basically is it's a giant neutrino experiment where they send off a bunch of neutrinos. In theory, we know these neutrinos can kind of oscillate into different species. And some of them might be the sterile neutrino. And so I guess you can look for sterile neutrinos in this experiment. The other thing is that you can also look for it in astrophysics. So dark matter sterile neutrinos, like looking for the right abundance of sterile neutrinos that would constitute dark matter, would actually be around the KeV scale, right there. It's allowed to decay, and then you can look for its signatures into photons and things like that. This is kind of one of the famous searches that was done for it, very controversial, but it's called, this is the picture of the Perseus cluster in X-ray. This is what people look for, I guess, dark matter particles like sterile neutrinos. The last exhibit that I'm going to talk about is the Axions. Okay. And so, kind of we come back full circle now from astrophysics to Axion. Right? The Axion is a hypothetical ultralight particle. It lies in ultralight region. So this is kind of more in the category of wavelength. It almost behaves like a light wave. It's actually a class of particles of which the QCD Axion is the most famous. QCD stands for quantum chromodynamics. This refers to the theory that we know of the strong force binding quarks together in gluons. And its main appeal and motivation is that it solves another problem called the strong CP problem in QCD, which is proposed. I'm not going to go into the strong CP problem, but very intuitively, the strong CP problem is at the most high level, it's like saying, why is my theory of quarks and gluons and this kind of messy soup of atoms so symmetrical in a sense? And nobody has a really good answer to this, but if they're axions, like a kind of the sea of invisible particles, like currents in the water, are pushing things together to allow them to be symmetrical, that's basically what the axion is. At a very, very high level, mostly, almost certainly somewhat incorrect, but intuitive kind of feeling of what the axion is. As an aside, this solves two problems. You can have, if you go on the preprint archive for physics papers today, I guarantee you there are a lot of people that are going to put out their own theories every day. You get a new theory of dark matter every day. Most people don't really pay attention to it because it's too much and it's not very well motivated. But once you have a model, a particle that can solve two things, then people become interested. And so all these classes of particles, solve multiple things. That's why they're motivated, right? Otherwise, you can come up with a million ways to like account for dark matter, but it only will solve that problem. It's not particularly interesting. Another way to say this is, there's too many people out, too many papers out there that kind of put out a model. These models take time to test, but there's too many of them. Let's focus on the ones that actually seem the most motivating. These, I think, in the literature, these are the ones that are most motivating. So this also appears in string theory constructions for people that are interested in string theory. But kind of a funny aside is that, by the way, this is kind of a diagram for what might the axion might interact with, like, like a neutron, like there's a down quark, and up quark would make up the neutron. It has something to do there. This is like a simulation that was done of like Axion strings. That's very, very cool. This basically, I've been told this is like a brand of laundry detergent, like cleaning detergent called the Axion. And that apparently was the inspiration for how people got the name, because they would clean out all the problems with particle theory. So this is what I've been told. I think that's correct. Anyways, that's where the Axion. So let me ask, is the search for dark matter just beginning? I'm a grad student whose work relies on the answer being yes. So I'm going to say yes, the search is just beginning. But I think there are actually really motivated candidates for dark matter, as you've just seen, and the fact that we can now search for this with 21st century data. And I think that's really significant, and I think it's very exciting to explore, what all these particles might, which one might be the dark matter, which one might exist, given the amount of data we have. So I'm going to blaze through this, the last chapter. It's not as long. Which is chapter 3, the science. How do we actually go and look for it? What do you go home and like, what experiments do you want to like go out and fund to look for these dark matter particles? How do we look for such a thing? First, you need to assume some kind of connection to the standard, right? This is a must. If you only have, like, we only know it because of gravity. If it doesn't interact with anything else, you'll never be able to observe it. You'll never be able to know its fundamental nature. Let's not think about that. Otherwise, we should go to other problems. But let's assume that there is some small connection to the standard model. That could be electromagnetism, the weak force, the strong force, etc. That means we'll have some hope of observing it. And I think there are good reasons, like the motivated models before, that tell us there should be some connection to the standard model as well. This is an involved diagram. I'm going to go through each step of it kind of as we go along, but it kind of tells you the different methods and ways that people look for dark matter in experiments and observations and telescopes, simulations. Let's start with direct detection. Direct detection is this thing on the right here, this black box. You read it from bottom to up. So you look at normal matter and dark matter, and you read it from bottom to up. So dark matter and normal matter come together and they scatter off each other. Is the picture clear there? This is what direct detection basically means. It means I'm setting up an experiment, and I'm going to have a dark matter hopefully come in and scatter off my normal matter. This is what people do in a lot of direct detection experiments. So you have these like big chambers full of like particles and nuclei and things like that, or like LZ, the xenon, where they basically have like multiple tons of liquid xenon, and they hope that dark matter comes in, scatters off of it, and leaves like some observable signatures like missing momentum or like other particles like radiation from light. There's also something called ADMX. Technically, it's a direct detection experiment, but it kind of works on a different mechanism. ADMX is basically a giant magnet that waits for axions to come in. And then there's like a theory that axions should interact with electromagnetism. So by being in a strong magnetic field, they'll somehow turn into a photon. And this is what they hope for. I don't think they've seen it yet, but they're working on it, as with everyone here in this field. And so this is what direct detection means, setting up an actual experiment.
So are you looking for behavior like a neutrino? This
Yeah,
axion is
basically.
gonna come zipping by just by accident?
Yeah, in many ways, the axion physics is very similar to.
But it's got a lot of gravity to it, so the neutrino has nothing to it.
Right. For the ultralight case, it's not actually that heavy. Like the axion is not a heavy particle intrinsically. It's an ultralight particle, but different from a neutrino. Neutrino is like a fermion. The axion is a boson, which means you can collect a bunch of axions in the same place at the same time. And that's what makes the dynamics different. But otherwise, it is very similar to neutrinos. You're waiting for it to come into like a magnetic field, and you look for an oscillation. Yeah, great question. Yeah.
The giant vat on the bottom right,
Yes.
I'm fairly certain is a xenon vat, and I'm fairly certain that's the one that's actually detected some stuff. But how do we know that the stuff it's detecting is dark matter and not something else?
This requires, that's a good question. I'm not sure if this is xenon. I think this is LZ and this is xenon. but maybe they, I mean, I'm sure they look similar because they
Yeah.
are similar mechanism, but that's a good question. And this is basically, they have teams of people doing background analysis, right? But you need to know that your signal actually came from a dark matter particle. It's not just like a cosmic ray came down and like did something funny, but we can still explain. And so there are like a lot of experts on these types of things. I mean, there's even experts that they hire that like, look for, I don't know, like vibrations, right? That could like shake up your nuclei and maybe cause some effect as well. So that's a good question. I'm not an experimentalist, so I don't really know how like deep they go, but they go pretty deep in terms of like looking at the background. Everyone. Yeah, as I'll show later, there's maybe I guess I don't know too much about the status of xenon, but I know LZ came up with it. Anyways, let's go to indirect detection. Let's read it from right to left now. You have dark matter particles that come in, and then they basically do something, annihilate or decay into standard model particles that we can see today. So this is actually stuff that I do mostly. So indirect detection basically just means astrophysics, looking at dark matter with astrophysics. You look at spots of dark matter and you hope, right, that they annihilate within themselves or decay within themselves to form things like light that you can then observe with the telescope. So there's a lot of different ideas that float around in indirect detection. There's like gamma ray astronomy, X-ray astronomy, radio astronomy. You can look for these signals from all these different types of models. White dwarfs, neutron stars, you can look at these types of things. Maybe they'll produce particles like the ones we're looking for, like give signatures of dark matter, or even just like random black spots in the sky that are very dark, because that's where dark matter should be most abundant. Or like that's compared to like, any backgrounds. This is like an artist's rendition of a neutron star. This is the Fermi telescope. This is like gamma ray telescope. It gives a very nice, like gamma ray view of the sky. This is the galactic center. It's a little galactic disk. Maybe there's dark matter particle signals in here. Who knows? People are very hard working on this. Then, this is like, for example, a starburst galaxy, which has a lot of very young bright stars that can maybe produce Axions. That was a piece of work with them. And so there's a lot of things you can play around with in indirect detection because
So you're kind of using the universe as your particle.
exactly. You use astrophysical objects as your laboratory. And I think it's really cool because you have a lot of telescope data now. You can test this. And then I'm going to quickly go over this colliders and cosmology kind of approaches. In some sense, they're kind of similar. In a collider, as someone alluded to, you basically collide things that normal matter, and then you watch for the debris. And if there's missing energy in the debris, you might have yourself a dark matter particle. Like that you can't really directly observe, but has to exist. Right? You said it's a level of inference, yes.
Aren't they doing that in the Large Hadron
Large
Collider?
Hadron Collider. Yeah. And actually, this is like a picture of, the
They
Alice.
try to like check if there's dark matter, and that's why they have those huge thick walls.
Yeah, exactly. Large Hadron Collider works very hard to smash particles that we do know together and try to look for any missing particles. Let's see, and then in cosmology, there's this thing, a lot of people think about like the universe annihilation, like how does dark matter affect how the universe evolved? And so in this sense, you can predict a lot of scenarios in which dark matter interacts with the early universe, and then this could be like some equilibrium or non-equilibrium, and then influence subsequent evolution of galaxies and galaxy clusters. And these are like simulations that people have done, when you inject like dark matter particles in the early universe, how does it affect the universe as we see it today? You can get some interesting information out of that. Again, this is a Large Hadron Collider. Presumably they're colliding a lot of particles together to try to look for maybe some dark matter particle that's flew away, but you can tell by the different energy. So a lot of different ways you can probe dark matter. These are the four main ways. And most ways you look for it are categorized under these. And kind of the current status of dark matter searches is, like if we discovered dark matter, you would have heard about it in multiple news sources already. But we haven't found it yet, but I think it's really just beginning, right? Now that we're actually understanding a lot of these models and how they interact with the data that we get in the 21st century, I think is going to be really exciting in the coming year. But there's many challenges to face ahead, both theoretical and experimental. But the search really does continue. Here is kind of, there was a recent result by LZ, notice that 2024. I was actually at this conference last month and they revealed it. And it was kind of, it was exciting because, it's like a really strong bound. The y-axis is basically how strong the interaction is with the WIMP and the nucleons in your detector, in the LZ detector. And it was kind of exciting to see that you get really strong bounds on, intuitively, because they didn't observe anything, dark matter must have an interaction that's weaker than this, which is important information. But I guess if you wanted to look for dark matter, it's not so fun because they didn't observe it. And then over here is kind of a plot, another great one by Kieran O'Hare, that basically lists a lot of the astrophysical ways, not just astrophysical, but mostly astrophysical ways that people look for axions coupling to like electromagnetism. They haven't observed anything yet, but what that tells us is that the interaction strength must be in the white region, things that we haven't probed yet, weaker than what we're able to probe. And so this is also valuable information as well. And so people keep searching, hopefully within the coming years, I say with more and more data and more novel ways to look for, these particles within data, you might cover a lot of the space and maybe even find some. And that would be very exciting. So to summarize, this is a nice picture, by the way, of the Milky Way, artist rendition, I think. Dark matter is one of these few problems in theoretical physics that we know a lot about despite not really knowing. I think this is really a kind of this philosophical kind of juncture in history in which we can be excited about this because it's so tangible, but there's still things left to do to know what it really is. Yeah.
Is the picture the side of the Milky Way?
Yes. It's like looking at the disk of it.
The middle is, or in every picture, the middle is always slightly
Oh yeah.
thicker.
Like that's why
Is it because of the black hole?
Well, I mean, when you look at it on Earth, it would be like slanted, right? Because it's the position of us on Earth. I think there are like you can send out space telescopes and they can get a different orientation. Like good question. Another thing about dark matter, again, we must know it has to exist from astrophysics. We know it's a real problem. It's not like a made-up problem. There are made-up problems, but like this is a real problem. And then there's an abundance of ideas in particle physics that would actually answer this. That'd be very exciting. Again, I'm very optimistic and very excited about dark matter. And I think people should be more than ever. Right? We have motivated candidates in a golden age. Dark matter would tell us again. If we solve this, it would tell us a lot about our place in the universe, how it evolved, and very importantly, would be like the first hint of beyond standard model physics in a long time. And I think it really will revitalize particle physics. It's last thing. This is a problem. It's a problem across multiple branches of physics, right? I'm speaking in as a particle physicist during Astronomy, but all of these things are intrinsically related. You can't attack. I don't think you can attack it from just one angle alone. And I think it'd be a really generational defining moment. Some might say glorious. If we were really to attack this problem and then maybe finally solve it within the coming decade, which I think many people are hoping. So thank you. I'm going to leave us with the truth is out there. I think the truth